Welcome to the online class BSc 4th semester diffraction session 5. In this session we learn about Fraunhofer diffraction at single slit. Here we learn the Fraunhofer diffraction, specific sort of a diffraction. Here Fraunhofer diffraction is a far field diffraction, and Fraunhofer diffraction is a plane wavefront. Fraunhofer diffraction, simpler maths. So as shown in the figure, Fraunhofer diffraction. So in Fraunhofer diffraction from a single slit, consider the geometry shown below. Assume that the slit is very long in the direction perpendicular to the page so that we can neglect diffraction effects in the perpendicular direction as shown in the figure. The radius of second half period zone is given by Pm2 is equal to square root of b plus lambda whole square minus b square. If we solve the square root, we'll get square root of 2b lambda. Generally, n minus 1th zone can be shown to Pm n minus 1 is equal to square root of n minus 1 b lambda. Equation 1. So the radius of nth zone is Pmn is equal to square root of nb lambda, equation 2. The area of nth zone is equal to the area of first n zone minus area of first n minus 1 zones. So if we substitute, we'll get pi is equal to nb lambda minus n minus 1 b lambda. Finally, pi b lambda, equation 3. Equation 3 shows that the area of nth zone is independent of zone number, and hence the area of each and every zone is a constant independent of the zone number. The radii of zones are proportional to n to the power of 1 by 2, even though the area of each zone is the same. Hence, the width of the zone decreases from first to the outer zone. The contribution towards the amplitude of the wave at O has the same value for each and every zone. Fraunhofer diffraction, whereas the mathematics is given below, where A is the width of the slit AB. Now the corresponding phase difference between the rays originating from extreme points A and B is 2 pi by lambda into A sin theta. Let the aperture AB be divided into a large number n of equal parts, each part being the source of secondary wavelet. The amplitude of vibration at P due to each part will be the same, say A, but their phase will vary gradually 0 to 2 pi by lambda into A sin theta. The phase difference between the waves from two consecutive parts is del is equal to 12 pi by n lambda into A sin theta, where n is the number of vibration. The resultant amplitude at P is given by R is equal to A sin n del divided by 2 into sin del by 2 is equal to finally A sin pi A sin theta by 2 into sin pi A sin theta by n lambda, equation number 5. So R is equal to A sin alpha into sin alpha by n, where alpha is equal to pi A sin theta by lambda. Since A by n is very small, therefore sin A by n is equal to A by n. So we have R is equal to A into sin alpha divided by alpha by n is equal to, finally we'll get capital A sin alpha by alpha, equation 7. Whereas A is equal to NA is the amplitude of all the vibrations in same phase. Now intensity at P is I is equal to R square is equal to A square sin square alpha divided by alpha square. For intensity to be maximum or minimum, d into d alpha A square sin square alpha into alpha square, which gives a square into alpha square sin 2 sin alpha cos alpha minus sin square alpha 2 alpha whole divided by alpha to the power of 4 is equal to 0. So finally sin alpha by alpha is equal to 0, or sin alpha is equal to 0. So a sin alpha is equal to 0, or alpha is equal to tan alpha. So this is the result. So condition for minimum intensity: when sin alpha by alpha is equal to 0, the intensity is 0. So sin alpha is equal to 0, alpha is equal to plus or minus m pi is equal to, which implies pi a sin theta by lambda is equal to plus or minus m pi. So which implies a sin theta is equal to plus or minus m lambda, equation number 9. So which gives the position of first, second and third minima corresponding to m is equal to 1, 2, 3 and so on. Here m is not equal to 0, because when m is equal to 0, then a sin theta is equal to 0, which is the condition of maximum intensity. So condition for maximum intensity: for maximum intensity alpha is equal to tan alpha. This equation can be solved graphically by plotting the curve y is equal to alpha and alpha y is equal to tan alpha as shown in figure. The abscissa of the points of intersection of these curves gives the curve required value of alpha, for which intensity is maximum. For central maximum, alpha is equal to 0. So from equation 8 we have I is equal to a square, or is equal to simply I naught, say. For secondary maximum, alpha is equal to plus or minus 2m plus 1 into lambda divided by 2, which implies pi a sin theta by lambda is equal to plus or minus 2m plus 1 pi divided by 2, which implies a sin theta is equal to plus or minus 2m plus 1 into 2 lambda. If we put m is equal to 1, 2, 3, we get position of first, second, third, secondary maxima respectively. Now putting m is equal to 1, 2, 3 in equation 11, we get alpha is equal to 3 pi by 2, 5 pi by 2, 7 pi by 2 and so on. Intensity of first secondary maxima: I1 is equal to a square sin square 3 pi by 2 divided by 3 pi by 2 whole square, which implies a square into 4 divided by 9 pi square, which implies 4 divided by 9 pi square into I naught, that is 4.5% of I naught. Intensity of secondary maxima: I2 is equal to a square sin 5 pi by 2 divided by 5 pi by 2 whole square is equal to a square into 25 pi square, which is equal to 25 into pi square for I for 4 by 25 pi square I naught, that is 1.5% of I naught. Intensity of third secondary maxima: I3 is equal to a square sin square 7 pi by 2 divided by 7 pi by 2 whole square is equal to a square into 4 by 49 pi square, which is equal to 4 by 49 pi square I naught. Thus the relative intensities of successive maxima are I naught ratio I1 ratio I2 ratio I3, which is 4 by 9 pi square ratio 4 by 25 pi square ratio 4 by 49 pi square. Thus the most of the light is concentrated in the central maxima, and intensity of secondary maxima goes on decreasing. In short, we can say that the diffraction pattern consists of bright central maxima surrounded alternatively by minima of zero intensity and feeble secondary maxima or rapidly decreasing intensities. So as shown in the figure, the intensity distribution curve. The intensity distribution Questions. Question 1. The areas enclosed between these circles are known as option A half period elements, option B half period, option C both A and B, option D none of the above. Answer is option A half period elements. So question 2. The radii of zones are proportional to even though area of each zone is option A same, option B different, option C both A and B, option D none of the above. Answer is A same. Question 3. In Fraunhofer diffraction of single slit, dash is used. Option A prism, option B lenses, option C mirror, option D none of the above. Answer is option B lenses. Question 4. Fraunhofer diffraction is a option A near field diffraction, option B far field diffraction, option C both A and B, option D none of the above. Answer is option B far field diffraction. Thank you.